Hi. A few weeks ago, I saw some Paraguayan PE42420 single-pole double-throw RF switch chip evaluation boards on eBay selling for cheap. So I got a few and wanted to take a look here. According to the datasheet, the PE42420 is capable of switching signal inputs and outputs between the two ports with a bandwidth of between 100 MHz and 6 GHz. And isolation is quite decent with a 50 decibels at 6 GHz and quite a bit better at lower frequency. For example, at 1 GHz, the isolation increased to a minimum of 69 decibels. Also, the linearity is pretty good with a third-order intercept or the IAP3 of 65 dBm. Now, RF switching can be done in many different ways. You can use an RF relay which can cover a wide range of frequency with very high isolation and very low insertion loss and exhibit no nonlinearity. And of course you can use a pin diode as an RF switch, or you can use a more integrated solution like the Paraguayan PE42420 that we are looking at here. The main advantage of a solid state device switch like this is a small size, low current consumption, and they can switch at an incredible speed. And due to packaging and die size limitations, these chips can't handle really that much power. For instance, this PE42420, the maximum amount of power you can put into this device, into its onboard termination resistor, is only at 20 dBm. Well, of course, the device itself can handle more power if the power is going through the device, which is rated here at 30 dBm. So the maximum power going through it is 1 watt, but if you want to terminate into the termination resistor on board, you can only input 0.1 watts. And the chip is really easy to control. If you look at the datasheet here, you will see that all it takes is the voltage applied to the two control pins. And by alternating them from high to low, low to high, we can control which way the single-pole double-throw switch is switched to. So I thought what we would do first is to take a look at the basic operation, and then we'll do a couple more experiments. And now this board is hooked up for our basic testing, and let me explain to you what we have here. So behind there is my bench power supply, which is set to 3.3 volts right now, and the power is coming in from these cables onto this test board. And the signal coming into the board is from the HP 8671A synthesizer up there. Now it's set to 2 GHz and currently have the power turned off. Because that signal generator synthesizer rather is unleveled output, and I have two 3 dB pads hooked in series so that I can reduce the output power, even though I don't have to, because this chip can handle a maximum of 20 dBm input, whereas the output from that is around 9 dBm at the maximum. But anyway, so now that coax comes down here and goes into currently I have it configured to go through this through calibration through. The reason is I wanted to see what cable loss is, and so later on we can take a look at what insertion loss is for this PE42420. And the output now goes to this detector, and that is hooked up to the WaveTech 1045. So right now, because if the power is off, it's showing minus 63 dBm. So now what I'm going to do is I'm going to switch the board using a jumper wire to switch the channel on and off. So to do that, I'm going to hook up this clip to control channel 1. And later on what I'm going to do is I'm going to hook this up to the ground so that one channel is grounded. And because internally these pins are pulled high, so the channel 2 would be enabled, and we should see that on the power detector here. So what I'm going to do is I'm going to readjust the camera to point to the power detector here. So now again we're at minus 63 dBm, and now I'm going to connect to ground channel 1. So 3 Oops, 3, 2, 1. And now you can see that the channel 2 is turned on, which right now we're at 1.55 dBm, which gives you about a just over 1 decibel of insertion loss, which is within the range of what the specification says. So that's pretty much how this RF switch operates. Now, of course, we can also test the other channel. I'm going to just actually, you can see here, I'm going to remove this input from the top side. So now I'm going to hook up to the bottom. And again, this port now becomes isolated. But if I hook this one to this next pin, ground the next pin, we should see, again, this channel now is turned on. So now we have seen the basic performance of this RF switching chip, which is a PE42420. And according to our experiments, everything pretty much falls in line with what the spec says. And also the basic operation, you can see that it does nothing more than switching the input signal between the two RF ports. Now I thought it would be interesting to do some experiments and using the board in a slightly different way than its original intended purpose. So let's take a look at the specification here again, and you will see that the switching time is at a typical 300 nanoseconds, a maximum 400 nanoseconds, which is very, very fast, much faster than any relay-based RF switch can do. So we can utilize that fasting switching speed and use this as a modulator to modulate a input signal. And for instance, on-off keying. And here is our setup for the on-off keying, or OOK modulation. And it looks a little bit of complex here, but it actually is very simple. So let me just quickly run you through the setup here. So up there again, we have the 8671 synthesizer output at 2 GHz. Currently is turned off. And in the middle, I have my WaveTech 395 set at a standard 1 kHz frequency, again turned off. And it's set up to be outputting a square wave at roughly 2 volts from 0 to the peak. And because the input to this 42420 is actually 1.8 volts compatible, so we only need about 2 volts to be able to control the input. And so that's the second synthesized arbitrary waveform generator. And in the middle, we have a spectral analyzer, and currently it's sweeping at a center frequency of 2 GHz and with a span of frequency span of 1 MHz. And finally, I have the oscilloscope there hooked up to the modulated signal. Well, not the modulated signal, but the signal to modulate the carrier, so that we can have a visual look of what the frequency of the input signal looks like. So let me set everything back a little bit, and we will start our experiment. It's a little bit difficult to put all the instruments into one shot, so I'm not going to show you the 8671A synthesizer. That thing is just outputting a 2 GHz signal anyway. But even right now, things are a little bit small, so I'll try to explain here. So basically right now, everything is off. So let me power on the synthesizer. Now the synthesizer will be outputting a 2 GHz signal. And as you can see from the spectral analyzer, we have a little bit tiny peak here. That's the leak through from the switch, and which is very minute, can be ignored here. So now let me turn on the switch, and you will see a big jump in that peak. So now the switch is on, and you will see we get a roughly 0 dBm output signal, which is what we had before. So what is going to be more interesting is when I start applying the modulation signal. So right now, remember, there's no modulation signal. The mains this output is off, and we have, just to remember the shape of the signal here. So now let me turn the modulation frequency on. and see what we have here. So as soon as we turn on the modulation frequency, we will see that the spectrum expanded a little bit. And if you have learned communication theory, you will know that the bandwidth of the signal is directly related to your symbol rate, which right now is at 1 kilohertz. So if we increase that symbol rate, we would see the broadening of this band signal. So let's increase it to 2 kilohertz, 3, 4, 5, 6, and we can keep going on, and you will see that it's actually started to expand. So we can keep going till we hit, let's say, 100 kilohertz, and we still have the signal. Because remember, the rise time of that switch is only 300 nanoseconds. So we can easily push this to roughly 1 megahertz modulation frequency. So we can keep going up a little bit more, and you get the idea. So the bandwidth of the signal keeps increasing because of our symbol rate is increasing here. So that's the characteristic of your typical on-off keying. Now, of course, the spectrum would look similar for a amplitude shift keying signal, the ASK. As OOK is just a special case of amplitude shift keying because of one of the carrier amplitude is 0 because you don't have the carrier. Whereas the ASK, you have 2 amplitudes for the same frequency carriers. So now let's decrease the modulation bandwidth. And we got our 1 kilohertz modulated on-off keying signal. Then I wanted to do one more experiment with this board. This time I'm going to use this PE42420 RF switch as a FSK modulator. So basically FSK is a frequency shift keying, and basically we have 2 frequencies. So as you can see right now I'm using the HP8642B to the left there, outputting a 2001 megahertz signal, and the synthesizer out there 8671A is still outputting a 2000 megahertz, which is 2 gigahertz signal. So these 2 signals are 1 megahertz apart. And so just to show you the setup again, so up there, that's the synthesizer. And in order to switch the 2 modulation ports on and off, I built this simple transistor inverter, basically, as you can see here. This inverter, there's nothing fancy, just a single 2N3904, and the input, which takes directly from that WaveTech 395, which is set to be 1 kilohertz right now. And the output, well, the input actually, 1 goes to the input directly. Sorry, let me just show it here. 1 goes to the transistor inverter input, and the other one goes to switch one of the port directly. And the output from this inverter goes to switch the other port. So at any given time, only one of the RF switch is on. So this is just a simple inverter configuration here. So right now the spectrum analyzer is set to a center frequency of 2 gigahertz and 5 megahertz, so that we can accommodate the 2 FSK signals. And one thing I forgot is now this time I'm just doing an aerial output here. So as you can see, let me zoom it out again. So the output this time from this RF switch is actually the center portion, and I just use a short wire as a piece of antenna. This is the receiving antenna on the spectrum analyzer. And the sensitivity of the spectrum analyzer, the reference level is set to minus 30 dBm, so that we can see that relatively easily. So of course, the oscilloscope is still showing me the modulating the signal that switches between the 2 frequencies. So it's a square wave. So right now the WaveTech 395 is off at the moment. I'm going to turn it on, and you should see the waveform on the oscilloscope, which is a 1 kilohertz square wave. So now let me turn on one of the RF source, which is my 8671A synthesizer. And now we can see there is one frequency peak jumping around. That's the 2 GHz one. So now I'm going to turn on the HP8642B at 2001 MHz. And now you can see both of the signals are present, and they are centered around that 2000.5 megahertz center frequency. So this is our FSK signal. And of course, we can adjust the, let me just zoom out a little bit so you can see the WaveTech 395. So now we can adjust the actual frequency here. And let's do frequency. So if we increase the frequency, we can see that the modulated signal changes a little bit, but nevertheless you can see the two peaks belonging to that FSK characteristic signal. So now this is the signal at a modulation rate of 20 kilohertz. So with these two experiments, you have seen that we can not only use this single pole double throw RF switch as the switch itself to switch between two RF signals, we can also use it as a modulator. And in the first experiment, you saw that we used it as an on-off keying modulator, and now you're seeing that this one, it can also be used as a frequency shift keying modulator. Now, of course, using an RF switch as modulator, the efficiency is considerably lower than your typical circuit, in which you typically would switch the RF on and off. And when the RF is off, the power is not being delivered to the RF generation circuitry. Whereas in our case, the RF is a constant wave. It is constantly on, and we simply switch it off by dumping the RF energy onto the onboard 50 ohm termination resistor. So in this case, we're wasting half the energy of our RF signal. But nevertheless, you can see that we can use the RF switch as our modulation device. So I hope you enjoyed the video and learned something new. If you liked the video, please remember to subscribe, share, and like. I will catch up with you next time.